Thank you in particular to our speakers, Tommaso from Entropica, Khoon from CQT, George, thanks for joining us from NRF, and Hanhee, Michael and Andreas, thanks for your wonderful talks earlier. So during this session, it's going to be a bit of a question and answer session. As you can see perhaps on the screen behind us, there's questions coming in on Slido. So if anyone in the audience is interested to ask a question, you can send it. You can join on this address, slido.com.
They should have a screen for us to see the question.
Oh, the prompter. Yeah, that's right.
Well, this way,
Then he's going to read
it. Jenny's moderating it, so there's hopefully nothing too nothing too controversial. Okay, so I wanted to start off by giving you each a minute to introduce yourselves. For those that don't know me, I'm Joe Fitzsimons. I'm a PI at CQT. But the real important people here today are the panelists. So maybe Tommaso, you can start by...
Is it on? Yeah. Sure, okay, so I'll say something more about myself than I said during the talk. So my name is Tommaso. I'm now the co-founder of Entropica together with Khoon. As I mentioned earlier, I've been in the quantum computing field for more than 8 years now. I have done my PhD in Sydney at Macquarie University. Started working on quantum gravity at the beginning and then quite quickly swayed towards quantum computation and in particular quantum information. While I was at CQT and SUTD, I was working together with Joe on delegated quantum computing and blind quantum computation, and especially in the last few years, maybe also partly influenced by Joe actually, I became more and more interested in this whole idea of really applying quantum computing to what people call real world problems. I'm really not a big fan of the real world label, but let me just use it for the sake of the argument, to really take the technology and start pushing it a little bit outside of the lab.
Hi, I'm Khoon. I'm, as Joe said, I'm a part of CQT. I'm a CQT fellow right now. And my primary institution is actually Yale-NUS college. So I'm a physicist and a theoretical physicist. As you can tell this morning, that part of my work is really on quantum error correction and fault tolerance. There's also a part of my work that my collaborator, Birger Ingrid, was sitting there and staring at me whether or not I was saying something unusual. That part of my work really involves quantum tomography, and this, of course, right now has a lot of connections with my error correction work because a lot of the questions that we are asking right now is about how do you discover properties of noise. Right? So this is where the tomography part of my life and the error correction and fault tolerance part of my life really come together.
I'm George Loh. I'm from National Research Foundation. I'm overseeing some of the research programs in NRF. I think the closest of my training background to quantum computers perhaps is my training in computer engineering, in industrial system engineering. That is only the computer is related to quantum computer. But I've been involved in quantum research through my NRF career. I'm on the board of CQT. Understand a lot what CQT is doing. Recently, we have just launched a quantum engineering program in September last year. So I was working with the local community to put together the quantum engineering program. It's a $25 million program. It's initial investment into quantum engineering. Right now, I'm working on a secretariat we have a task force on quantum engineering led by the government chief scientific advisor for Ministry of Trade Industry. We are doing looking forward what Singapore should invest in quantum engineering. So I'm helping and as part of the secretary to support that task force. So as you can hear, that the government is actually putting a lot of focus on quantum technology.
My name is Hanhee Paik. I'm a physicist at IBM Research, IBM-Q. And I've been working on superconducting quantum computing since Andreas was a postdoc, because I was a student, he was a postdoc, so you can imagine how long. And My recent project was developing 16-qubit IBM-Q, the QX machine that I just introduced, and I'm interested in, again, hardware, improving the performance of the hardware.
Hi, I'm Michael Bremner from the University of Technology, Sydney. I work in quantum algorithms and complexity, but also in helping establish milestones in the development of quantum computing architectures for experimental teams in various places around the world, but mostly in Australia. I've been in this field for 18 years now, and yeah, I know, right? Yeah, and like I said, I work in the Centre for Quantum Software and Information at the University of Technology, Sydney. That research centre has a very heavy computer science focus, but we do things pretty much all the way from quantum control and optimal control for systems through to developing theoretical program languages for quantum computers. I also work in the Australian Research Council Centre of Excellence for Quantum Computation and Communication Technology. That's got a much more experimental focus. So I work in a theoretical program there, but the big focus there is on developing silicon qubits and optical qubits for quantum computers.
Okay, so my name is Andreas Wallraff. I'm an experimental physicist at ETH Zürich in Switzerland. We run a lab with maybe around 20 students and technicians and staff to build superconducting circuits, both for sort of basic exploration of quantum physics, but also for applications in quantum information science. And in Switzerland, we do have a large quantum information science and technology program since 8 years now. And with our lab, we are part of a big US program on realizing error correction in superconducting circuits, and also other labs with ion traps. And our lab's also part of a big European initiative to build a quantum information processor, which had just launched its first round of projects in October last year.
Okay, so perhaps I can start off by asking each of you a couple of standard questions before we get into the audience questions. So I think maybe a burning question for many people is where you see the field going in the next 5 years and maybe 5 years beyond that. So, maybe 10 years time coming towards 2030. How do you see the development of the field then, where we're likely to be in terms of hardware, and also, what other important developments we should expect within that period. So maybe we can start off from Tommaso again and work across.
Sure. Yeah, it's a good and tough question. So maybe focus a little bit more on the algorithmic software side. What I would like at least to see, and what I hope we are going to see in the next 5 years, is really the development of, at first, more fundamental tools for quantum computing. Again, being inspired by what has already been done in classical computing, and not trying to replicate, but at least trying to follow a similar path. Also, I think it's of course crucial to have a strong evidence of quantum advantage within the next 2 years. I believe that will happen. And again, there will be a bit of back and forth between quantum and classical computing, because most likely, even if it happens, it's not going to be the last word. It's very likely that classical computing group will come a few months later and say, we managed to replicate it, which means that the ball goes back into the quantum core. From the hardware side, I will not say too much, but there is one thing that I really would like to see as part of the hardware development in the next, let's say, 5 to 10 years, which is something I mentioned before during the talk. It's the concept of a quantum realm. And that goes back to something that Patrick was saying during his talk, this intrinsic difficulty of encoding classical information inside a quantum computer. That is, of course, crucial for any machine learning or any data analysis task, because if we want to analyze data, the data needs to physically be in the quantum machine. And in order to do that, you need to have a very good way to do it. I'll just say quickly and easily. So I think it's extremely crucial to see development not only on the quantum hardware, which has been advancing very fast, but also on all those parts that are needed and are not directly related to the QPU, to the main processing unit.
much about 5 to 10 years from now because that's too far in the future and cannot possibly predict. But I think in the next 5 years, what we are going to see and what I hope to see really is for us to move far beyond the first steps of quantum computing hardware. Yeah. I mean, people who have been in this field for the last 10 years or maybe even longer than that will have heard the fact that we have been saying that we have a quantum computer in decades, and we've been saying that for decades by now. So I'm not thinking that we will have a quantum computer in the next 5 years, but I really hope to see that with really a lot of these activities is coming online now, we will be able to go beyond really just the first demonstrations because we have taken many first steps by now, and it's really time for us to start taking the second step, the third step. And then the question is, what are some of the obstacles that we will encounter along the way in these harder steps when we get towards really the ultimate goal, right? So this is what I hope to see really in the next 5 years or so.
I'm not going to look into crystal ball and try to predict where the quantum computer will be in the next 5 years, as I'm not an expert. But if looking out, looking in from an outsider, as a funder, as an investor, as a user, what I'd like to see in the next 5 years is actually to see what advantages quantum computer can give to, I hate to use your term, real-world problems, or really problems that the day-to-day that we are facing, that perhaps the current classical computers or supercomputers couldn't solve them, whether in the next 5 years we could identify some of them that would say using quantum computers to solve them would give us some advantages. I'd like to see that in the next 5 years, while we're pushing the boundaries of more qubits on the quantum computers, we also look at whether we could integrate quantum qubits or quantum subsystems on classical computers, having hybrid, where some of the algorithms that cannot solve problems for the classical algorithm that cannot solve the problems, perhaps can push the quantum subsystem to solve it. As hybrid, that there will be, you said it's a quantum RAM, but I would like to think about perhaps it's an accelerator or some kind of GPU, quantum GPU or sort of sort that could give us real advantage that we take the second step, third step, but we don't want to wait to the ultimate quantum computers to gain all the advantages. So I'd like to see in the next 5 years to 10 years that we could really have a hybrid of architecture between quantum and the classical computer. And the third thing that I hope to see while we push forward for quantum computer is to really understand how to program when quantum computers arrives. Classical programming, I mean, in the old days is really difficult. So I hope that through 30 years, when we into classical computing, that moving into quantum computing, that will help us to accelerate how we can do programming on quantum computers even before the real ultimate quantum computers arrive. Yeah, that's all.
So yeah, I also get that question a lot about the future perspectives, but I mean, I'm not sure. I'm not, it's hard to tell, right? At the same, it's hard to tell. But I know that we have some challenges to really move forward. And actually identifying those problems are actually kind of more important to me, so like a researcher who's working on hardware development. Because without solving the challenges, we're not going to proceed, right? We're not going to move forward. And one of the few challenges that we really need to solve in the next 5 years is we gotta improve the gate fidelity. That's sort of concern. I mean, I think the old platforms, it's not just the superconducting qubits, but also the ion traps. And again, the gate fidelity improvement, it's a single metric, but right now, to do that, we have to improve coherence, we have to improve the control. There are many different things. I mean, and then, probably the coherence limit could be ultimate limit for our gate fidelity. In the sense, for the solid state qubits, like a superconducting qubits, I think we may be hitting the material limit for our qubit performance. And material development is something, it's not going to happen overnight. So I'm hoping, I think there's some, the development that in the US and then also in Europe, I heard that you're going to focus some material, we're going to start some material research initiative or something like that in Europe, and then I think there are a lot of people are also in the US thinking that we have to develop the material for quantum applications. Again, I think that that's probably what's going to happen. Like, maybe we have to kind of push forward in the performance of the gate fidelity metrics, and then maybe developing like a next generation materials for the next generation quantum devices.
Okay, that was a really good answer.
But you have to talk about theory,
Okay, from a theory point of view, I think what she said. No, in all seriousness, from a theory point of view, I guess, what I would like to see happen over the next 5 years is a lot more, the integration between the high-end theoretical computer science side of like complexity theory, formal programming languages. I'd like to see a bit more of that integrated into the real-world application development. So we're already beginning to see that. There's been a lot of progress in quantum chemistry stuff over the last 12 months, and we're beginning to see a lot more crossover there. I think that's definitely yielding benefits. I want to see that continue. I want to see people identify really clear problems which are actually kind of interesting, that maybe they can't be done on 100 qubits, but they could be done on 1,000. The other side is also material science. There's like heaps of things there where there could be a lot of application. So that's, from a theoretical point of view, one of the things I really care about. The other is fault tolerance, which, from your talk this morning, basically exactly what she said. That's exactly what needs to happen. We need to think really hard about what are the best use case scenarios for the right kinds of codes in the right kinds of architectures. That's absolutely a thing that needs a lot more attention. It's a hard problem, and it won't necessarily get you like a high-profile paper in a top conference or a top journal. What we actually need is like the grinded out work of working out the details of fault-tolerant architectures, and that's just hard work. So that's sort of theoretically what I think is really interesting. From an experimental point of view, I think I'd like to see some progress from some of the architectures that aren't superconducting qubits or ion qubits. Like, I'd like to see the continued development of silicon and optics and quantum dots and some of these other qubits, and see if we can sort of develop. Because there's a possibility that those qubits may, have different properties and might be better at some things than some of the other architectures are. And I think that's a thing that we need to continue to pursue. But I'm not going to put a time frame on any of that.
Yeah, okay, so maybe first I would note that we do have quantum computers, yeah, so you can access them in the cloud if you want to. They're very small. They might not outperform classical computers, but they do exist. So they allow us to explore the capabilities of these computers and to play with them. And I think one way in which this makes a difference is that you now not only can go into labs and experience quantum physics yourself. Yeah, so like in our lab, we can have students who just go there and they make a superposition state and they see what happens when they create it and when they perform measurements. The same thing with an entangled state. And that for the most part of the time that quantum physics exists as a theory, that was just not possible. And now it's possible, and people can learn how to do that, and then also can find interesting ways of things to do with that. Yeah? And this made it, like the fact that IBM put their systems into the cloud made this feature, and IBM and others now made this feature available to everybody who wants to try it out. So that in itself is already very exciting, and I think it's a good prospect. But then I do think one advantage is also that this whole field is exciting as a field, independent of its applications, whether they're useful or not. Yeah, I think most of us, or maybe all of us, think that the research that they're doing is very interesting. I think we all find that at least as interesting as particle physics and astrophysics, and that's why we do it, even if nobody will earn money with it anytime soon. So what is it that we need? I think probably currently there's enough resources around there, there's money around, and you can make progress, and what is needed is good people who turn that money into actual progress. So maybe the biggest need is more education in this field, educate more quantum physicists and more quantum engineers to help us make more progress. And then I think that we'll see some improvement in these devices. I think the real challenge is actually on the hardware side, not so much on the software side. To build a large-scale quantum computer will be enormously enormously challenging. And I also don't think that IBM or Google anytime soon will build one with millions of qubits. Yeah, I think that's just, I think we don't know how to do that yet. One on the theoretical side, I think what would help though is to come up with more interesting use cases. Yeah, use cases that people would really be interested in paying money for solving their problems, like showing that you could use a quantum computer to make a better drug, for example. And yeah, so I think these are challenges to work along, and I think this field is very exciting because it is both interesting for the basic sciences, but it also does have this interesting application in a domain which is information processing, which really governs a large fraction of our daily lives. And I think that's what makes this field special and also attracts so much interest currently.
Thanks. So I'm going to switch now to a couple of questions from the audience. And actually I spotted one that came in quite recently that I think relates to the previous question. And it says, rather than predicting the future of quantum computing, what do you think we can learn from the history of quantum computing? I might extend that to say, what do you think we can also learn from the history of computing? Do any of you have any particular strong feelings about this, or any insights you'd like to share?
I think one very interesting story that comes to my mind about classical computing, and I believe, I'm not sure whether this is apocryphal or not, but I believe this quote belongs to Watson by IBM when he was asked, and when he was speaking about the first computing machines, I believe this was in the 50s, he made his forecast saying that there will only be a handful of these machines around the world for the next decades. Nobody's going to use them. We're going to have 5, maybe 10 here and there to solve very fundamental problems, and that would be it. And of course, this is not what happened. Then history changed. I mean, then history told us a very different story. So I think what we learn from this story is that, first of all, it's very hard, if not impossible, to predict the future, as we were saying. So this is the first thing, but also that a lot of unexpected use cases came with classical computing, that today we give them completely for granted. We think that we know how a computer should be used, and we are very confident about that. But the reality is at the beginning, and when I say at the beginning, I really mean 60, 70 years ago, not thousands of years ago, people didn't have such clear ideas. Actually, people didn't have good ideas at all. And today we are in a very similar situation. We are building these devices, they seem to be extremely powerful, and we still don't really know what to do with it. And I think what is going to be extremely exciting is that we're going to find a lot of applications that are highly non-trivial and that we haven't even thought of yet. And this is something very nice to learn from the history of computing.
So maybe I would add like maybe a hardware-related comment to that. So if you look at the integrated resources that were spent in bringing silicon technology to where it is currently, yeah, that's enormous. Yeah, there's billion transistors that are on our chips currently. They didn't come for free. There was a lot of investment of time and research and just resources overall into making this happen. And I think the reason why it could happen was because the previous generation of these chips funded the development of the next generation of these chips. And I do think that we're probably, in quantum computing, we're probably safe for the next 5 to 10 years. I think there's enough resources around to continue this development, make the next steps. But at some stage, we will need to find one application that somebody's actually willing to pay for, and make sure that we can invest some of the revenues of that into making the next generation. And I think if we can't identify that type of use case on a reasonable time scale, I think it will be hard to make this a commercially viable activity, which does not mean that governments could not pursue this further, even on a longer time scale in their research labs or big companies for their interests or universities. Yeah? But if you wanted a big commercial success, that's probably needed on some time scales, which is maybe 5 to 10 years also.
I just have a few views about whether it's quantum computers or just typical sub-problems that we're solving. I think the fundamentals, the foundation that we have built for quantum sciences and quantum sciences, information science over the hardware they are building, I think we need to continue to do that and build up to a certain capability that it can solve a problem. I mean, it's capable enough to solve a problem. If you look at CMOS and all the silicon hardware architecture that we took for granted today, because they solve a problem, but we wanted to solve it better. So there's certain fundamental capabilities that you solve a problem, but it's not good enough. So we go back to basic research and make it better, and then you bring it to the real world problem again and make it better. I really hope that one day will come for quantum computing that there are enough hardware and software for us to solve a problem. It may not solve it elegantly. Then we need the scientists to go back and build better quantum computers and better software to take us to the next stage. I think that hopefully that will be the evolution for quantum computers.
So maybe I could ask a different question. Given that there are these lessons to maybe learn from history, one thing I might ask is what areas people, in your view, should be working on at the moment but aren't? What do we need that we're not doing at the moment? Does anyone want to take a shot at that?
Sure. Well, going by those answers, it sounds like there needs to be a lot more focus on algorithms research. So one of the challenges, which you might have gathered from my talk, is that really developing applications which have a clear advantage over classical computers is very theoretically challenging. And part of the reason for that is we have a very poor understanding of the capabilities of classical computers. So we really need more research. We need to encourage more people to study like theoretical computer science, which is a thing which has kind of ebbed and waned over the years, and teach those people also quantum computing at the same time. And this is the thing that we really need to focus on over the next few years, in my opinion, if we want to solve those sort of problems. I should also say, though, I think the motivation for why you want to build a quantum computer, like having a clear application would be great. Like that's awesome. You know, we can put a dollar value on it and say this is worth this much money. To me, the bigger incentive is not necessarily that, but rather Moore's law is coming to an end, and we don't know what to do next. And the entire economy has got used to the progression of Moore's law. And we need to find something to replace that growth. And that's quite an important problem. And it allows for potential significant disruption in the whole computing industry. So for me, like that's the really big reason why investment is flooding into quantum computing.
Let me use the answer that actually Alex Ling had mentioned to me about coffee break for this question of what is it that we are not yet doing, which is really systems engineering. Okay, and what I mean by that, and what we were discussing earlier, the coffee break was really the fact that yes, you can come up with the best qubit technology, and you can come up with the best algorithm. At the end of the day, actually, there's a lot of engineering work that it needs to go in to put all those qubits together into something that can actually run those algorithms. Okay. And I don't mean just in terms of looking at the physics part of it or something that is about reducing the noise. I really mean about really building it up as a system. If you look at what, for example, a classical chip company, or look at what Intel is doing, for example, you look at the number of engineers that they hire really just for putting things together, devising how to connect all your different pieces together so that they function reliably, function in the manner that you want. There's a lot of work that needs to be done there. Okay, I cannot say what is really the in terms of research motivation, in terms of whether or not you get this published in famous journals. This I don't know. Okay, but I really think that this is one area that we need to focus and have people really start thinking about these ideas.
Okay, so moving on, I guess I can ask another question that seems to be particularly popular on Slido, which is, as a relatively small country, how can Singapore distinguish itself in this area? So I'll put up the full question. So So the question as written is, how can Singapore differentiate itself in quantum computing from big countries like the US, EU and China? I'm not sure if any of you have any views on this. Another question is, that is very related to this, is whether there are any areas in Singapore that are either particular strengths or particular weaknesses that are critically underrepresented that we may need to strengthen going forward. I wanted to ask what your views on this are. I think given the panel we've got people from both inside Singapore and outside Singapore, from industry and academia and from funding agencies, so maybe we are in a good position to get some interesting answers.
Okay, I can say something about us as a startup. One of the challenges that we will certainly face at some point is how to bring the talent that we need here. I mean, there is talent here, but quantum computing even within CQT remains relatively small, and this is true actually worldwide. I mean, the community is still very small. So for us, a big challenge will be being able to attract people away from the big poles that are going to be China, Europe, and US. And I think this is, despite the challenge, this is where Singapore could really play a role and could really shine, because today and for the foreseeable future, Singapore still has an attractiveness that other countries in the region might not have. And I think this is something that as a country should really play in their favor to establish a strong pole. Especially during my talk, I was discussing how, despite the size of the country, there is already quite an active ecosystem of startups here, so we should really, maybe you can say something better about what is the best policy to do so. We should really think of a strategy, of a common strategy to attract people here and to make it a place where people really want to work and think of working for quantum computing. I think that is really crucial. At the end of the day, I think that the real need in the field is still people with great ideas, people with great expertise, and people with the willingness to really undertake challenges that are not simple. So we need to attract the people here, which is a big challenge, but is also a big opportunity because of the role that Singapore has played in the last 50 years in the region.
This is a question that can be used in any forum, whether it's quantum computing, AI, or cybersecurity, blockchain, blah, 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 right? How can Singapore as a small country differentiate ourselves vis-a-vis the big countries like China, US, and Europe? Or should I add vis-a-vis companies like Google, IBM, Apple, Alibaba, and Einstein, and so on, right? That is a generic question, but so I can give a generic answer that would apply to actually any area that Singapore wants to be in. Now, Singapore government invests about 1% of GDP in R&D. As a country, as a percentage of our spending is quite high, 1% of GDP. Over lunch is quite interestingly, I was talking over lunch, having lunch outside today, and I was told that Alibaba is spending over 3 years, about 15 billion over 3 years, just on R&D. Singapore, our 1% of GDP is not to compare with 5 billion US dollars from Alibaba. We just cannot compare. So what could we do really to differentiate ourselves? Now, of course, we want to invest in emerging and state-of-the-art of the research that is exciting. So we attract people, talent to come. Now, Singapore established CQT about 12 years ago, maybe 11, 12 years ago, something like that. Even before quantum was such a hot topic, right? So we invested, and we believe that basic sciences are important so that we can attract talent. Now, it is the same when you attract talent, because it's difficult research problem, talents are coming. So similarly, you need to give them different problems to solve. Now, if you build certain technology, use certain research outcome, then you need to say, this is a very difficult problem. Who can solve it? And I think interest doesn't come only places as money. I mean, we have only 1% of GDP, but if we could be a good test bed for challenging problems, then I believe talent will come to Singapore. That you would solve the problem with good technologies, whether it's systems, devices, or more, and then that would be a lot of use. And that's where more startups would develop and come off and fill the gap and provide services. So I think that is one of the things that is very important for Singapore to do, is to invest in the right area, because 1% of the GDP is not a lot. Now, beyond R&D, we have to take care of healthcare, we have to take care of transportation, blah, 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 blah. So we need to use it very, very judiciously. Having said that, we continue to invest in area of research that is important, that's interesting. Now, coming back to quantum computer or quantum engineering, Singapore is a hub for advanced electronics. Now, silicon or photonics or silicon on chip is coming to an end. Now, so what is the next phase for Singapore on manufacturing or even advanced microelectronics? Now, quantum engineering is an area that is a lot of excitement. So it's something that the government is putting a lot of interest and investment in it to make sure that it could perhaps take up some slack if the silicon is not going to improve anymore. So this is where we hope, and you can be sure that we invest in basic research as well as, should I say, real problems to solve. So yesterday I was at one of the Nobel laureates forum, and one of the speakers was saying, now research is like a circle. So basic research is a point in the circle, so is applied research, depending on your perspective. So you do your basic research, then it's a circle, come to the point of applied. But the problems may be too challenging for your outcome, the technology, that you need to go back to basic. And so it's a circle. I like the analogy very much, because there's no clear differentiation between basic research and applied. It's really on continuum.
Can I ask, do any of our overseas speakers have an opinion on this? Maybe coming from outside Singapore, you can see things that us locally may not see.
So I think one thing that one could consider, for smaller countries, Switzerland is also a smaller country on the grand scale of things, which invests a lot in research and education. But in particular, if you look at it from a public perspective, you could consider teaming up with other countries, maybe having a joint initiative. Yeah, so not every country is building their own accelerator to find the Higgs boson, for example. And couldn't afford it either. So maybe one question to think about is whether one should team up in some form to get some of the big challenges related to quantum information processing tackled in a collaborative effort. Yeah? An interesting thing to also notice is that maybe the quantum computer itself is not expensive in itself. Very expensive. What you pay for is the cost for developing it. Yeah, I guess if IBM wanted to give you a copy, maybe I shouldn't say that. I know what the hardware really costs, but if you wanted to just buy the parts and make a copy of that, and IBM was going to give you a chip and the software, you could probably have a copy of your 20-qubit chip that would maybe cost, I don't know, close to $1 million or so. And say even with a 100-qubit processor, you could probably get it for $2 million or so. Just the hardware cost of it. So the real cost is actually in the development of these things. And maybe trying to get a return on that investment that you made. Yeah? So, but this makes it, for example, different from building a big particle accelerator, so which probably has both of those. So if you could get together with your resources and in a public way develop things that are important in quantum information processing, and then maybe share some of the high cost for doing these chip developments, and in particular chip fabrication or so, that could allow also smaller countries or even, individual universities and academics labs are in the same position here. Where will they get the chips from that allow them to continue research in this area? And also now, if you have semiconductor research or integrated circuit research at universities, they don't run their own CMOS process. Yeah, they do the designs and then send it off to some foundry. And probably something like that will be needed. And probably IBM won't make chips for everybody at all the universities and who wants to do research with it. So maybe that could be one thing to think about.
By the way, you can join IBM Q network. Anyone interested in IBM hardware, then the door is always open. So like a few years ago, I reviewed a program of some country that I'm not, because I wasn't sure what I signed, and then I'm not sure whether I can reveal the name of the country, but probably can guess. So they are trying to start a quantum program, and I was one of the review to, look over the program overview, the designs. And then when what I saw was they're putting sizable money, there's a lot of money there, but then they're trying to do every single aspect of a quantum computing, quantum information, quantum communication, and quantum sensors. So, but then right now the country doesn't have a quantum program, and they don't even have a quantum people. I mean, probably less people than Singapore. So my advice was the focus. Again, if they wanted to catch up on the quantum technologies, and if they don't have people yet and infrastructure, why don't you focus on a few, and then develop, to put investment there, and then to try to develop, right? I think maybe Singapore could take that strategy. You can probably put some focused area of the whatever that works the best, and then you can put your investment there, and that's usually just good strategy too anywhere. But I just wanted to make some comments because I recently learned about history of Singapore, so I went to museum, actual museum, and probably no one thought about. So when Singapore was separated from Malaysia, I think everyone was kind of poor, and probably no one thought about you guys gonna be like. I mean, right now Singapore is one of the leading, a very developed, very advanced country, right? But then probably no one thought about that when Singapore was separated from Malaysia, right? But again, you guys worked hard, and when I see the audiences, it's very diverse. Probably more diverse than, many of the US universities I've seen. And I believe this diversity also could draw very talented people. I mean, for example, right? People are everywhere, and you have a very good infrastructure. And I think also Singapore government can also focus the many different, technology aspects that basically that really draws many talented people from the overseas. So I believe that I think there's a very bright future if you guys are jumping on the quantum technology. I mean, especially you have a CQT. This is a really great, the base, right?
Yes.
Yeah.
So, if you don't mind, I'll change from the kind of outlook and policy side back to technology and say, pick up another question from the audience, which basically says that we've heard a lot about superconducting qubits today, and that's obviously a reflection of choices made by the committee organising this event to invite two superconducting experimentalists to talk. There are a lot of other technologies that are being considered for quantum information processing. There are certainly a number of ion trappers in CQT, as well as people working on optics, for example. But this kind of leads to the question: what's likely to be, what's likely to take the lead in the medium to long term in terms of quantum technologies? There was some really interesting news, I guess, about a month ago from IonQ, where they had demonstrated very high fidelity gates on a large system with a large number of qubits. And I wanted to get your views on what you think the prospects are for different technologies, what you think will take the lead. I assume Mick is contractually obliged to say it's going to be silicon.
Or optics. Okay, so apparently that's been thrown to me because these experimentalists probably won't answer this. I mean, I don't think we really know yet, would be what I would say. And I think this is a thing which we need to pay heed of. I think right now there's a temptation to think that what's in the lead now, which I think is unquestionably superconducting technologies, will be forevermore. But I can remember 12 years ago, or certainly when I started in the field, superconductors were not the leading technology. And superconductors have overtaken ion traps in some sense, and they've got into the lead. And that could totally happen again with other technologies, but I don't know which ones they will be, because there's a lot of actual basic science still happening. There's a lot of issues with, say, for instance, silicon, there's potential there, but there's like many experimental hurdles people have to overcome, and fabrication hurdles people have to overcome. Likewise in optics, there's similar issues. So I think it's hard to tell, and I'm not sure I'll pick a winner. It's silicon, but I don't know what the real answer is.
So maybe one aspect of it is that I do think that, for example, the silicon-based technology and superconducting circuit-based technology, in the end, they're not all that different. Yeah, they get operated at low temperatures, and that's because the typical frequencies that they are worked with is in the gigahertz range. You need control electronics, you need micro and nano fabrication. So I think in the end, these two are sort of complementary in a way that you could even switch between them at some point if you find out that one or the other turns out to be better. I think ions are also doing very, very well currently, and they could maybe even performance-wise do better than superconducting circuits. And then in the end, it will boil down on many details. Yeah? And maybe I could see that maybe on the say 10, 20, 50 qubit level, maybe ions can perform even better than any of the solid state realizations. But on a really large scale, and when you think hundreds and thousands of qubits, I do think that ions will probably have similar problems as solid state circuits with introducing extra need for optical frequency control fields, and whether one will really be able to successfully tackle these challenges. I think this is not known yet. Yeah? But could it be that ions will do better for identifying sort of a midterm solution to say some NISQ era problem with 50 or 100 qubits? I think it might well be that they could be doing better than solid state realizations at this time scale.
Okay, well, I think we've a couple of minutes left, so I'm going to deviate from the questions from the floor and ask you a personal one. I mean, for me personally, it's not about your personal lives. So, what I want to ask you is, what way in which do you think investment in quantum computing and quantum technologies can change things? So, if the scale of investment in the area was to drastically increase, so if you look at the current figures being invested, even by the European flagship project and things like this, it is small compared to the scale of the amount of money that went into developing the iPhone, for example. And presumably building a quantum computer is harder than building an iPhone. So you know, a question is, what difference does money make? If there was to be much larger scale investment, will that change things? Does that shorten the timeline? Or are there barriers that will remain there independent of the scale of investment? Does anyone have a view on that?
I did say already something in this direction previously, and I currently don't have a startup company, so maybe I have a little less incentive to say that we need much more money. I think, for example, if you're set at a certain scale, like a university lab or so, I think many labs can be doing quite well with the resources that they have, and I know that ETH Zurich is maybe in a bit of a special place in that. Yes, I think there's not many people who complain not being well funded there. I do think that the real bottleneck, and I've mentioned it before, is finding enough people who are qualified to actually bring the field forward with the additional money that they could use. And I think and that's really the thing that makes the big difference for making more progress. Yeah? Getting well-educated people with research experience or with experience in these areas into the field. And one thing that I think we see a little bit happening now is that, say, graduate students and postdocs with experience in the area who have maybe graduated a few years back, 5 or 10 years back, who've then not found or were not looking or have not found jobs in sort of the industry because it didn't exist then. I think those could come back now and continue to work on quantum technologies, and that could make a difference. And as well as educating more students in a certain area. So one thing that I, for example, noticed since a year or two is that now all the students that come into our lab, they all know about machine learning. Yeah? And that just like a year ago or two, that just wasn't the case. Yeah? And if maybe in 3 years they all know about quantum computing and are excited about it, they could really make a big difference to turn more money into more progress.
Let me give some personal view. It doesn't represent the government or NRF view. I think that's qualified. So I think talent is one. I fully agree to make progress in quantum computing or quantum technology. I think talent is key, but I'm not going to go into that. But I would think that we need to put out enough capabilities in quantum technology. I use the word technology in general sense, hardware, software, algorithm correction, even communication kind of things. Enough technologies and building blocks up there that we could use it for a certain use. I like your example of iPhone. Now, when the first generation iPhone came out, it looks like other phones, except it has a bit more capabilities. But iPhone evolves because as we use it, there are certain inadequacy. There's certain constraint that is not giving enough capabilities to do the things we want to do. And then, of course, the company takes off and evolve it. So if quantum technology is to improve progress, I would think it's important for the scientists to put enough quantum technology and then find a use case for it. And understand the limitation and constraints and go back to basic again, develop more technology and capabilities, and then we push forward. And then it will just evolve.